Hello, let's start with section 3.2. Now we're going to graph using both the first and the second derivatives. So before we do the second derivative, let's talk about concavity and what does concavity mean. Okay, so if a graph is concave up, that means it opens up. And if a graph is concave down, that means it opens down. Okay. Wherever the concavity changes, we call that an inflection point. Okay? So the second derivative tells us all about concavity. If you remember last time we did the first derivative tells us whether the function is increasing or decreasing, right? So decreasing. It tells us whether the original function f is increasing or decreasing. The second derivative tells us whether f is concave up or concave down. If your second derivative is positive, that means your graph is concave up. If your second derivative is negative, that means your graph is concave down, and an inflection point is where the concavity changes. Okay? The point at which the second derivative is 0 or undefined, let's put that in here, or undefined, is called a stationary point. Okay? A stationary point is not necessarily an inflection point. So if the second derivative is 0 or undefined, we call that a stationary point. If the concavity also changes at that stationary point, then we call it an inflection point. Okay? So all inflection points are stationary points, but not all stationary points are inflection points. So it says a stationary point is not necessarily an inflection point, but all inflection points are stationary points. Okay? So if you remember, this is like parallel from last time, right? The first derivative, we found wherever the first derivative is 0 or undefined. Let me write that better. Wherever the first derivative, so f prime x, equals 0 or undefined, from that we get the critical numbers. The second derivative, wherever the second derivative is 0 or undefined, from this we get the stationary points. Okay. Some books say critical number, some books say critical points, same thing. Okay. Let's look at an example. A company's annual profit for after X years is given by this function, which tells us millions of dollars. Excuse me. Excuse me. Graph this function showing all relative extreme points and inflection points. Interpret the inflection points. First thing we have to do is make a sign diagram. Before we can make a sign diagram, we have to find the derivative. So let's take the first derivative. 3x squared minus 18x plus 24. Okay, and we want to set that equal to 0. When we set that equal to 0, so we set this equal to 0, and let's factor out a 3. X squared minus 6x plus 8 equals 0, and then we get x minus 4 and x minus 2. Set that equal to 0, and then we get our two critical numbers. Okay. Now let's do our sign diagram. And we want x equals 2, so that's my first critical number. X equals 4. That's my second critical number. Now, what I want to do is I want to plug test points into the first derivative, remember? So let's pick some good test points. Before 2, let's pick 0. And again, we are plugging this into the first derivative. This is a sign diagram for the first derivative. Then let's plug in 3, and let's plug in 7. pick any numbers. No matter what numbers you pick, the y values will be different, but your arrows should be the same. So if you and your friend pick different test points, your arrows should look the same. So let's go ahead and plug these numbers into y equals. So my function is, I'm sorry, we're going to plug this into the derivative. So the derivative is right here, 3x squared minus 18x plus 24. Okay, and I want to use the table feature to plug in the values that I chose, 0, 3, 7. So we get 24, negative 3, and 45. Oh, right. So 3x squared minus 18x plus 24. I just want to double check my numbers here. 0, 3, and so 24, negative 3, and 45. So the first derivative is positive, which means my graph is increasing. Here at the critical point, the derivative is 0, which means it's flat. Here it's negative, decreasing, flat, positive, increasing. Again, you're looking at these numbers, right? This is positive, up, negative going down, positive going up. Okay? So second, find the relative max or min and write them as ordered pairs. So let's look at the shape of the graph. What is actually happening? Well, this is going up and then flat and coming down. So here I know I have at 2, I know I have a relative max or a local max. This is going down, getting flat, then coming up. So here I know I have a local min. Okay. So the max, let's plug 2 into the original function. Whoops. Oh dear, what happened? These are the old notes. Okay, let's plug. Alright, let's try it again. Let's plug 2 into the original function, and we have a min at 4. So we're going to plug 4 into the original function. Okay. So where's my original function? Right here. X to the third. We can do this by hand. It would probably be faster, right? So if you plug 2 squared is 4. I'm sorry, we're plugging this into the original function. 2 cubed. So 2 cubed is 8 minus 9 times 2 squared is 4 times 9 is 36 plus 48. 24 times 2 is 48. Okay, and we get 8 minus 36 and plus 48 gives me 20. And then I plug 4 into the original function here. You can also use the table setting like I did before. I'm just saving myself some time. So 4 to the third, 4 times 4 is 16 times 4 is 64. Minus 9 times 4 squared is 16. Plus 24 times 4 is 96. Okay. 10 times 16 is 90. 9 times 6 is 50. What is it? 64. So that's 144. Okay. And you should get 16. Okay. So these are my 2 points. 220, sorry, I lost my train of thought for a second. 2, 20 and 4, 16. Okay. And again, this is your max and this is your min. Okay. So we found the relative max and min. We wrote them as ordered pairs. Okay. Now it says make a sign diagram for the second derivative. Well, now let's take the second derivative. So for the second derivative, let me just copy the first derivative here. 3x squared minus 18x plus 24. That was the first derivative. So the second derivative should come from that. We take the derivative again. We get, let me write it here, 6x minus 18, right? And then we set this equal to 0. We solve, we get x equals 3. Now also we have to see where is this undefined, right? Because that also gives us the stationary point. We call this a stationary point. And this is defined everywhere. So I'm going to say undefined nowhere. Right? It's a polynomial defined everywhere. Same thing with this one. So the only way we can get critical numbers and stationary points is by setting it equal to 0. If we had rational functions, which we'll see later, then we'll... Alright, oops, sorry about that. I had somebody come into my office. So let's see, where were we? So when we'll see rational functions, we'll see that you have to also take where the derivative is undefined, or the second derivative is undefined, to find these stationary points and critical points. Okay, so let's make a sign diagram for the second derivative. Now what I like to do, oh good lord, I don't know what's up with my computer. So let's see, pen, this. And what I do is I always write what the sign diagram is for. So this is for the second derivative, so I'm putting f double prime here. My stationary point is x equals 3. Okay. Just like up here, excuse me, I wrote f prime, so I know this is the sign diagram for the first derivative. So as you're doing your work, it's good to write this so it helps you remember, stay on track. Alright, this we know is a stationary point. Again, we're going to do the same thing like we did before. Plug values, but this time we're plugging test points into the second derivative. So let me plug 0, that's easy, right? That's an easy value, and 4. So when you plug 0 into the second derivative, 6 times 0 minus 18 gives you negative 18. When you plug 4 in, 4 times 6 is 24, minus 18 gives me 6. This is positive, so therefore, sorry, negative 18 is negative, so therefore my graph is concave down. 6 is positive, therefore my graph is concave up. Did the concavity change? Yeah, it did. So this is not only is it a stationary point, but it is an inflection point. Okay. If the concavity had been down, down, or up, up, that means the concavity did not change, and we would leave it as a stationary point SP. You would not write IP. Okay. Now it says find those stationary points and write them as ordered pairs. So what we need to do is plug 3 into the original function. Okay. So let's plug 3 into x cubed minus 9x squared plus 24x. That is my function. So we get 3 times 3, which is 9 times 3 is 27, minus 3 times 3, which is 9 times 9 is 81, plus 24 times 3 is 72. Okay, so 27, so 81, so 153, so 27. Something, yeah, also minus 81 plus 72. Sorry, so that's going to give me all together, I'll get left with 20. Oh no, not 20, 18. Oops. Alright, you can also do this on your calculator. I'm just trying to avoid flipping between screens. Sometimes that messes up the computer. Alright, so we get, so our stationary point, our inflection point rather, and our stationary point is 3, 18. Okay, now we can sketch this graph. Okay, so our inflection point is 3, 18, and our critical points 220 and 416. So 1, 2, 3, 4, 220. So let's go by 4, 8, 12, 16, and 20, and 1. Okay. So 220, 2 and 20 was our first critical point. Our second critical point is 416. 4 and 16, which is here. Okay. And before 2, it's going increasing, flat, down. So increasing, flat, down. And then it's going to go decreasing, flat, up. So that goes decreasing, flat, up. Okay. So that is our relative, this is our relative max, this is our relative min. And remember, our critical point, our inflection point, sorry, was 3, 18, which is roughly here. Notice how the concavity changes, right? Before the inflection point, we have concave down, which I have here. After the inflection point, we have concave up, which I have here. Okay? So everything matches, my graph matches my sign diagrams, and that's lovely. Okay, so that is what the graph of that looks like. Let's look at some problems in your book. So this is on page 197. Let's look at this one. For each curve, is there an inflection point? So you want to ask yourself, does the concavity change? Okay. So for this one, this is concave up. This is concave up. Is this an inflection point? No. And I don't know how to write on this screen, but the first one would be no. Okay, it's not an inflection point. The concavity does not change. How about this one? This is concave down. This is concave up. So yes, this is an inflection point because the concavity changes. Okay. Let's look at the same page, inflection points in the real world. Okay, these are very cool examples. So this function is essentially the graph of net income for AT&T over recent years, shown on the left. So notice that the inflection point, so what's happening here, this is the year and this is in billions of dollars, their income, right? So their income is increasing, it kind of flatlined, then it started decreasing, okay? And then at some point here, it's still decreasing, but that's like the sign of the upturn, right? Notice that the inflection point represents the first sign of the upturn in AT&T's net income, which occurred in 2003. So I'm not sure why it happened in 2003. Maybe that's when they got into the business of cell phones, okay? Or internet, okay? Internet provider coverage. The graph on the left shows the annual sales of portable MP3 players, okay? The inflection point. So let's see what's happening here. This is millions of sales. And you can see it starts off pretty slow, but then in 2002 takes off, right? The sales of portable MP3 players just shoots way up. And then right around 2000 and before 2005, right after 2004, we see it starting to slow down, and it gets really slow. Okay, so the inflection point marks the end of the period of increasing rapid sales growth, and the first sign of approaching market saturation. Okay. This is when savvy manufacturers might begin to curtail new investment in MP3 production. My guess is that this is when our iPhones, right, our phones became more, capable of handling songs, so we no longer had a need for portable MP3 players because our phones could do it all. Okay, so notice here the inflection point, right? This is rapid growth. This is growth, but the growth is slowing down after the inflection point. And the graph on the left shows the annual sales of analog cameras. Remember those cameras that required film? A few years after the introduction of digital cameras. The inflection point occurs in 2004. So let's see here. Millions of sales. It started off roughly 18-20 million, and it's slowly declining. And then all of a sudden, it's 2004. Something happens. It marks the end of increasingly steep sales decline and the first sign of steadying but lower sales. So you can see this is slightly concave down, and now it looks like it's turning slightly concave up. We still have an inflection point there. Okay. So basically, there's when you're looking at increasing, decreasing, concave up, concave down, there's only basically 6 situations what your graph can look like. If your graph looks like this, right, or like this. So if your graph is increasing, this is the first derivative positive. It's increasing. But the second derivative, what's happening to the second derivative here? Well, let's give an example. Let's suppose f of x, now this is the original function, f of x is something like 3x, right? That's a linear function. The first derivative will be 3, whoops. The first derivative will be 3. The second derivative will be 0, isn't it? So when your graph is a line, the second derivative is 0. Same thing, this one, the first derivative is negative, and the second derivative is 0. Okay? This is what the f can look like, the graph of the original function. So if it's not constant up or constant down, then it has to be curved. This is increasing, right? So the first derivative is positive, but it's concave down, so the second derivative is negative. This one is also increasing, so the first derivative is positive, but it's concave up, so the second derivative is also positive. This graph is decreasing, first derivative negative. This graph is decreasing, first derivative negative, but it's concave down, second derivative negative. This graph is decreasing, first derivative negative, but it's concave up, so the second derivative is positive. Okay? Now there's something called the second derivative test for relative extreme points. Okay? So we say x equals c if it's a critical number at which the second derivative is defined, then what you do is you take your critical number and plug it into the second derivative. If you take your critical number, plug it into the second derivative, you get a positive number. That means your graph is concave up, isn't it? And that means you have a min. If your second derivative is negative, that means it's concave down, so you have a max. Let's do an example. Use the second derivative test to find all relative extreme points of this function. This function is the same function we had before, okay? But let's go ahead and do just less like it's from scratch, okay? Use the second derivative test. This should tell you, first thing you need to do is find those critical numbers, okay? That's an S, by the way. So the critical numbers, let's find the first derivative. We did that, we got 3x squared minus 18x plus 24. We factored and did all that good stuff, set it equal to 0. Our critical numbers, look at this. Set it equal to 0. Our critical numbers equals, last time we had what? 4 and 2, right? 2, 3, 4. So 2 and 4 were our critical numbers, and 3 was our stationary point from before. I'll just say from above. Okay. Now the second derivative test says take your critical numbers and plug them into the second derivative. So we need to find the second derivative, which was 6x minus 18. And then I'm going to take the second derivative, I'm going to take the critical numbers and plug them in. So 6 times 2 is 12, minus 18 gives me negative 6, which means my graph is concave down, which means I have a max. Max at x equals 2. Same thing for the second derivative here, plug the critical number in. 6 times 4 is 24, minus 18 is positive. 6, that's positive, so that means it's concave up. So that means I have a min. Min at x equals 2. Okay. So the min is at x equals 2, but once you have to take your 2 and plug it into the original function, that gives you the actual minimum value. And then, ooh, I made an error here, my apologies. This should say 4. Min at x equals 4. Okay? From here. So f of 4, oh lordy, it is too late. My apologies again. This should say f of 2 gives the max value. Okay, so let's do this again. You take the second derivative, plug in 2, you get negative 6. This is negative, that means it's concave down, so you have a max at 2. Once you plug 2 into the original function, that gives you the max value. When you take 4, which is a critical number, plug it into the second derivative, you get 6, which is positive, so that's concave up. So we have a minimum at x equals 4. Take 4, plug it into the original function, and that gives you the minimum value. Okay. Now, one thing I want you to notice here. Okay. It is possible, here our max is the higher value, 220, and our min is the lower value, but it is possible to have a function that looks like this. Okay, this is another example. It is possible to have a function looking like this. So your max is not your absolute max, but it's your local max, right? These values here are larger than this value, but this is still called the local max, and this is a local min. Okay. Similar to what we have here. Alright, so these are some directions to sketch a curve. First thing you want to do is find the domain, right? For rational functions, find the vertical and horizontal asymptotes, and then find the first derivative and all x values at which the first derivative is 0 or undefined. That's our critical numbers. Make a sign diagram showing the first derivative. Find the second derivative and set that equal to 0 undefined. That's stationary points. Make a sign diagram for the second derivative. And then based on the sign diagram, sketch the graph. Okay. Sketch the graph of f of x equals x to the 5th, or a cube root of x to the 5th. I'm sorry, square root of x to the 5th using these steps above. Use your own paper. So let's go ahead and do that. Okay, so here I have the function. Let me write it as x to the 5/2, makes the derivative taking easier. Okay. Again, let's look at our steps. Let me close this off. So let's look at our steps. Find the domain. Okay, so now we want to know the domain of this function. Is there anywhere where this function is undefined? Well, this is a square root function, right? So it has to be only valid for positive values of x. Okay. Then the next thing it says is, for a rational function, find and graph any vertical or horizontal asymptotes. We don't have that. Now let's find the first derivative. Okay, so I'm just basically going to go through and follow these steps. So no horizontal asymptote or vertical asymptote, since f is not a rational function. Okay, you don't have to write that on an exam or quiz, but I'm just showing you in the notes. Okay, then we want to take the first derivative. So 5/2 x, 5/2 minus 1 is minus 2/2, which gives me 3/2. Let me rewrite it as f, and this is, oh, I'm sorry, 5 square root of x cubed divided by 2. Okay. Now for the critical numbers, we want to set this equal to 0. Okay. And when we do that, we get, I'm going to multiply both sides by 2/5. So I get 0. Oops. Multiplied by 2/5, multiplied by 2/5. So then the 2's are gone, the 5's are gone, I'm left with this, right? And then we're going to multiply both sides by, or take the cube root and then square it. So when you take the cube root and square it, you still get x equals 0. Okay, so x equals 0 is our critical number. So now let's do a sign diagram for the first derivative. So f prime, x equals 0. And let's go ahead and plug in values. Let's plug in -1 and let's plug in 1. When we plug in -1, we get undefined, right? Because we cannot take -1 to the, where is it here? Again, f prime x is 5/2 square root of x cubed. So when you cube negative 1, you still get negative 1, and then square root of negative 1 is not defined. Okay. Here the graph is flat, and when you plug 1 into the function, 1 cubed is 1, square root of that is 1, you get positive 5. That is increasing. Okay. So we know that our graph, our original function f is going to look like this, or it might look like this, or it might look like this. We know it's increasing. Let's do the second derivative, and that'll tell us which shape it is. Okay. So the first derivative was 5/2 x to the 3/2. Bring the 3/2 out front, we get 15/4 x to the 1/2, which is 15 square root of x over 4. Okay. Again, you set this to 0, multiply both sides by 4/15, square it, and you get x equals 0. Okay. So that is also a critical number. I'm sorry, not a critical number, a stationary point. Let's see if it is an inflection point. So x equals 0 is our stationary point. We're going to take a value and plug it into the second derivative. When we take these values and plug them into the second derivative, which is 15 root x over 4, plug negative 1 into here, undefined. Plug 1 into here, we get 15/4. That's positive, so that means it's concave up. Okay. So now let's find what's happening at 0. When we plug 0 into this function, into the original function, it's 0. 0 to the 5th, square root of that is 0. So let's draw the graph. So at 0, we have 0, and then it's increasing and concave up. So that means it looks like this. Okay, and that is the function. Last thing we have to do is find all critical numbers of this, and then use a second derivative test to determine whether the function has a relative max or min at each critical number. So first thing we want to do is find the critical number. So let's take the derivative. Now this is the same thing as 1/4 x plus x to the negative 1. So the derivative of that will be 1/4 minus x to the negative 2, which is 1/4 minus 1 over x squared. Okay. Where is this undefined? The first derivative is undefined at x equals 0. Okay, so that is a critical number. Remember, when we plug 0 into here, we get 0 squared, so we get 0 in the denominator. And then we also want to set this thing equal to 0. Okay, let me add, let me add 1 over x squared to both sides, so we get this. Okay. X squared. And then you multiply both sides by x squared, multiply both sides by 4, you get this. So then you take the square root of both sides and you get plus or minus 2. Okay. You can go back and do the algebra, please do that. Okay. I'm not showing all the algebra steps because at this point I expect you to be able to do it. Okay. So you can, in your notes, you can stop the video and fill in the algebra steps if you need to. So we found our critical numbers, right? What are my critical numbers? -2, 0, and 2. It says use a second derivative test. So before that, we have to find the second derivative. Okay. So the derivative of 1/4 is 0. The -2 comes out front, that becomes +2 with this negative, and you get x to the -3. So this becomes 2 over x cubed. Now what you want to do for the second derivative test is plug in the critical numbers. So let me change the color. Plug your critical numbers into your second derivative. Right? So then you do f double prime of -2, f double prime of 0, f double prime of 2. When we plug -2 into here, Negative 2 cubed is positive 8. I'm sorry, negative 8. 2 over negative 8, so then this gives us negative 1/4. At 0, when we plug 0 in, it's undefined. At 2, 2 cubed is 8. So we get 2 over 8, which is positive 1/4. Okay. So look, my second derivative is negative. That means it's concave down. That means I have a max at negative 2. Okay. And here my second derivative is positive, which means it's concave up, which means I have a min. So we can write that. Min at x equals 2, max at x equals negative 2. Okay. So that's what the question said, whether the function has a relative max or min at each critical number. You can find the maxes and mins by doing f of 2 will give max, or that is the max value, and f of negative 2, that is the, f of 2 is the min value. Careful here. Is the min value, and then f of negative 2 is the max value. Okay, and you can find those. The question does not ask for it, so you don't have to. Okay, so that is all for section 3.2. Next time we will start 3.3, which is optimizations, and then we will go into word problems with optimization. Okay, so we're getting to the really good fun stuff. So if you have any questions, please let me know. Thank you for watching.